Reinforcement learning has shown promise in the control of single agents. However, coordinating multi-agent systems through RL still poses significant challenges. Among them, a critical one is non-stationarity, which occurs when independently learning agents change their policy during training. My name is Joshua Bloom, and in this work, we explore how to circumvent non-stationarity without resorting to agents having explicit knowledge of each other's actions and states through our method, global state prediction. A recent idea for dealing with non-stationarity is belief. Wu introduced spatial intention maps, which combine with agents' observations to provide spatial information about other agents' actions. Verlenu and Stolp utilize their own policy to reason over other agents. Jacques and Ndoso reward causal influence over other agents' actions. Belief methods require reasoning over other agents individually. GSP reasons over the aggregate, considering all agents at once, rather than one at a time. This allows for a problem simplification as well. By removing the need to consider the other agents, we are able to reason about the environment from a single agent viewpoint with partial observability. For this, we introduce aggregate centralized training with decentralized execution, where agents' observations and actions are implicitly assumed to be directly influenced at every time step. Agents' local experiences are stored in a shared replay buffer and sampled by a single policy during training. At execution time, this policy is copied and placed on each robot. GSP works by communicating a subspace of each agent's observation space. We will use collective transport as our task, with the MARX bot as our agent in simulation. The MARX bot has a series of 24 proximity sensors by which it observes the world. We allow agents to communicate their average of their proximity values. GSP takes these averaged proximity values and outputs a prediction on the state of the aggregate. In this case, it is the delta change in the orientation of the aggregate. This is then input as an observation, along with the other local observations, into an RL network. This work, we consider DQN, double DQN, DDPG, and TD3. However, this method is viable with other vanilla RL methods, such as PPO. Our action network then outputs a change in wheel speed for the robot to execute. We consider a 20-meter by 10-meter environment split into 3 zones. The zone on the left is the aggregate generation zone, where the robots and the object to transport are generated in a random location with random orientations. The zone in the middle of the environment is the obstacle generation zone. We consider 2 obstacle types, a cylinder obstacle and a gate obstacle. The cylinder obstacles are generated randomly with either 2 obstacles or 4 obstacles present. The gate obstacle is generated randomly along the horizontal dimension, and the opening randomly generated in the vertical direction. The zone on the right is the goal zone. The goal remains stationary throughout training and testing. Here we show the results for 2 communication approaches. Implicit communication, IC, is the emergent communication present based on the aggregate push and pull on the object to transport. Here we show in all methods, testing on all obstacles, a net increase in successful transports to goal. The bottom 2 figures on the left show the difference between a DQN policy trained with and without GSP. Notice the policy trained with GSP is able to avoid the obstacle with no collisions, whereas the policy trained without GSP collides with the obstacle, causing a failed attempt. The bottom plot on the right shows the learned strategies when trained with GSP. The plot on the top shows the orientation of the aggregate rotating away from the obstacle, and the plot on the bottom shows the aggregate performing a locally suboptimal policy, resulting in a successful trial by moving away from the goal at the midpoint of the environment in order to overcome the gate obstacle. Thank you to my advisor, Professor Pinsaroli, and to Aperti Mukherjee and Pranjal Paliwal for their contribution to this work.